Hello my friends, this is part 6 in a series of videos on bipolar disorder, and what I'm going to do in this 6th video is show you the results from the hypothesis test that was conducted in 2024, just in the past few weeks. I'm making this video in September 2024, just completed this hypothesis test. It's an updated version of what was done several years ago and was published in the book. Now, this hypothesis test is very limited in what it will tell us. It's limited because the model was built from analyzing charts of the clients of Giselle that she's worked with for many years. We have a lot of detailed information about their bipolar disorder, and then 912 charts of people with bipolar in a database. In the hypothesis test, we have only 69 charts, and only, I think, 64 that are C accuracy or better, and even fewer with A accuracy and better. The 912 people are AA data. The Gauquelins had their birth certificates. Wow. So we have only 27 charts with AA data. Now, research on 27 or 50 or 60 charts, data points, is just not as good as 912. So this hypothesis test is very limited in what it could tell us. Research is constrained by your resources. If we had lots of researchers and tons of money or whatever, we could go out and collect more data. But even people who have tremendous resources, you always have constraints of what you can do. So you have to work with what you have. So we're very limited in what we can do with having only 69 charts, 64 with C accuracy or better. So what we're going to do is we're going to do the best we can with the data we have. And in this bottom paragraph, I say, to compare the results of the test data, that means the 69 charts, with the training data, that means the 912, we see if the effect sizes are similar. There's basically two kinds of information that tell you how good your results are. There's the p-value, the statistical significance, and there's the effect size. Here's a simple example. Suppose you measure the height of all women in a country, or say you're in the United States, or let's say in France. You measure the height of all women in France, and they're 5 foot, this may be unrealistic, let's say they're 5'5", I don't know what it is. And in Germany, they're 5'6". So they're 1 inch taller in another country. Now, that would be tens of thousands, many millions of people if you only sampled 69 people out of those millions, and the French women were 1 inch shorter than the Germans. How confident are we that they're actually 1 inch shorter? We have no confidence at all. You can't tell from 69. Statistics tells you exactly what your probability of getting the results are. So if the women in one country were 6 inches taller, you'd have more confidence. That's the effect size. The effect size is the difference. Are they 1 inch taller, 6 inches taller? So when you have a relatively small group of 69 versus a large group of 912, what I wanted to see is, do these 69 people score higher than the control group by the same amount? Are they scoring by it's like saying, are they still 1 inch taller? Are we getting the same result? Because it's what we call the power of the test, is the statistical language. If you have a small sample size, you have less power, which means you get lower statistical significance even with the same effect size. Even though you found the same exact thing with the small amount of data, the statistical significance isn't there. So I looked at the effect size. I also looked at what the p-value is. I did that in this research over the past few weeks. So I'll show you all of this. So here's the effect size. With the 912 people, this is in the book. It's in Table 10 in Chapter 8. So if you have the book, go to Table 10 in Chapter 8. You'll see it. It tells us that the experimental group mean, that means the people with bipolar disorder, the 912, their average score, mean means average, their average score is 50.19. The control group was way down at 45.8, much less. And on the 79 people, the mean score was similar to the 912, actually slightly higher at 50.48, and the control group was actually slightly lower at 44.85 instead of 45. So the difference was even bigger for the 79 people in the test group than the 912 in the training group. And if you divide the 50.19 divided by 45.8, you get 1.096, which means you're 0.096 higher. The people with bipolar disorder are scoring 10% higher on the AstroSignature. Now, 10% isn't huge, but when you have 912 people, the probability of that is less than 1 out of several million. Now, what's a little almost bizarre is that the effect size, measured as the mean of the people with bipolar divided by the control group, was even greater. It was, instead of if we round this off to 2 decimal points, instead of 10%, 0.10 would be 10%, it was a 13%. It was actually better. That never happens. I mean, when you test a formula, you always have some what we call overfitting. It's not going to work as well in your test. It's not going to work better with your test data than your training data, because your training data is you built a formula that fits those people. And now you're going to generalize it to new people. You expect to go down. And in the book, I said if we get an effect size that's 50% or better, like around 0.05, that would be okay. If we got 0.07 or 0.08, 0.8, that would be great. But higher, that's crazy. But remember that there's a lot of random fluctuation with only 79. So I'm guessing, it's reasonable to guess, that this was a random fluctuation higher than really exists. So if I collect another 79 people, I'm expecting this to come down at least to 0.09, maybe even 0.08, or even 0.07. Because your model is going to work better with new charts than the previous charts, especially because the new charts are different kind of people. The first ones were people in Paris, France, in the early to mid 20th century, in a hospital, diagnosed with bipolar. Now we're in a different context, different situation. They didn't even call it bipolar then, they called it manic depression. Different circumstances. There are many kinds of bipolar disorder. There's 3 basic kinds. But anyway, there's just a lot of different situational things. It's not exactly the same kind of people. So probably from a research scientist standpoint, we suspect that if we get another 79 charts, we're going to get something in the range of 0.08, 0.09. Maybe it'll come out random fluctuation even a little lower. So when we run with the new data, the 69 people, we get a ratio of 0.090, similar to the 0.096 for all of them. When I removed the ones with dirty data, the DD or the X, I have only, oh, this is a typo, it says 62, it was 64. 64 charts, we get almost identical, 0.091. So we're right around 0.09. When we removed the C accuracy, it jumped all the way up to 0.148. And then A accuracy or better, that's 49 people, 0.087. And with only the top 27, went all the way up to 0.17. So they're in the range of 0.09 to 0.17. Similar to the 0.13, also seems to be a little bit inflated. I really don't think if we get a whole new 70 charts, I expect it to be closer to 0.08, just because it doesn't make sense that it's going to work better with new charts than the ones we used to build it. It's just very unusual. Now we have 75% overlap of the new data with the old data, and so that's probably keeping it a little bit inflated. Surprisingly, it's really just about as high with the new data as with the existing data. You could argue it's a little bit less because we had 13% with all 79, and here we have only 9%. So if you just look at only all the data, there was a drop from 13% to 9%. But we also expect, if the birth time is more accurate, for the results to be a little bit higher. And among the top 3, B accuracy or higher, and A accuracy and AA, we have varying from 9% to 17%. Here we're just at 9%. So overall, about the same. Also, one more thing about this. The control group means are fluctuating more than the experimental group means. If we take the average of all of these means, 25.15, 25, it's 24.85, then these are the effect sizes. And they're staying right around 0.10. In fact, to 2 decimal points, they're all 10%, one of them's 11%, and then it jumps up to the 17% for AA accuracy only. So using the mean of all the groups, that is probably even a better estimate, because the means shouldn't really vary depending on, I made a new control group for each one of these. And so, the control group mean is somewhere around 24.85. That's what people get if they don't have bipolar disorder. So bottom line is that we're getting an effect size of about 10%. Modestly, that's what we got with the original data set, 10%, and we're getting that in the replication studies, actually a little bit higher than 10%, all the way up to 17% with AA accuracy only. A lot of random fluctuation, so it's confirmed. We confirm the findings, conclusion, the findings reported in the book are confirmed. Okay. I have a note here at the bottom of the screen. The inability to find the original data is because I'm not able to find it in the current Astro Databank. Maybe it's there, I'm just not finding it, or maybe it was removed, I don't know. So that required this additional analysis, and so now it's better documented. We have this data, and it just confirms the results. That's what we expected. Now, I want to mention a very important detail. This hypothesis test with 69 charts, only 64 with C accuracy or better, and even fewer with higher birth time accuracy. Very small compared to 912. It's not a complete hypothesis test. We would need a larger sample size, at least 300 or 400, so that we can look at the p-values and the effect sizes. When you have such a huge difference between sample sizes, you cannot really compare. You cannot compare p-values because you have less power. You're going to get a lower p-value. That's why I compared effect size. It's a more reasonable thing to compare. So at the bottom of this slide, in bold, and this is an important point, it is impossible to properly compare a study of 912 data with another that has 69 data. It's like apples and oranges. But we compare it as best we can. In research, we use what we have. Nobody has infinite amounts of money and resources and whatever. So you work with what you have. This is what we have. We do the best we can. That's it. It's just the reality of it. So I look at the effect sizes because that makes more sense. You cannot compare p-values. If we compare the p-values and you only have 69 charts, which is the case here, you're going to end up with much worse p-values. Instead of 1 out of several million probability, with the same results, same effect size, same difference, the p-values are less. But just to document it and to confirm that, what I actually did is we made 5 control groups for each level. So this value here, I said the control group mean is 25.15. We actually created 5 control groups, took the average of them, which is a way to get a better average score for people that do not have bipolar disorder. And I ran the t-test and with a one-tailed p-value. In most of my research, I use a two-tailed p-value just to be extremely conservative. You're allowed to use a one-tailed p-value. It gives you results that look twice as good, but it's reasonable to do. Theoretically, it is one-tailed because we know what direction we're expecting the experimental group to be higher. Anyway, if you're not familiar with one-tailed, two-tailed, don't worry about it. The point is this. Using a one-tailed p-value, these are the p-values that I obtained for the 5 control groups for C accuracy or better, for those 64 charts. I didn't want to use the dirty data and whatever. We don't, the birth times are probably totally wrong. You need a fairly accurate birth time. But to have a fairly large group, I use C accuracy or better. And here's the p-values. 0.10, 0.15, 0.20, 0.25, 0.25, an average of 0.19. It's not statistically significant. We want 0.5 or better. So there's a 1 in 5 chance that the findings we got are random fluctuations. The point is this. Again, I'll say it again. I could say it a million times. It is impossible to properly compare a study of 912 data to another study with 69 data. We got the same effect sizes, actually even slightly better, with the test data, and the p-values are not significant. We could have gotten that randomly. It's not statistically significant. So our hypothesis test is not a ironclad, rock-solid hypothesis test. The sample size is too small. We got what we expected. We got even better than we expected. But is it scientifically conclusive that this bipolar disorder AstroSignature works? Yes or no? No. It's not scientifically absolutely conclusive. So why are we so excited? Why did I call the book a scientific breakthrough if it's not completely conclusive? Because we have built a new model that's been confirmed in many stages of research. At every stage, confirmed, and applied with clients, appears to work well there. This is called an evidence-based practice. And the question is this. Is it more likely that the AstroSignature is real and it works, or it's not real? That's my question as in an evidence-based practice. My question is not, have we gotten such high confidence that we can now say astrology produces measurable results? No. But what we can say is it's more likely true than false. Whoa. Nearly every leading scientist, I mean, over 90%, whether it's Neil deGrasse Tyson or whoever, popular scientists, or Robert Sapolsky, the great neurobiologist. These are people who are present on YouTube, for example. Great scientists. Both of them have said astrology is baloney. I mean, it doesn't work. I mean, there's no scientific evidence for it. I mean, nobody knows what's true or not true, but there's no scientific evidence for it. False. There is scientific evidence for it. That's what this book is about. That's why it's a scientific breakthrough. Is I completely and absolutely disagree with Neil deGrasse Tyson and Robert Sapolsky, both of whom I love. I just think they're just brilliant and wonderful. But there is scientific evidence. Is it overpoweringly convincing? No. Is it more likely that this AstroSignature actually works and can discriminate between people with bipolar disorder and those who do not? Even if only mildly, can it do it? Yes. We are very confident that it can. It's more likely that it can than it cannot. It's better than 50% probability. And it's the accumulation of every step along the way, including the research that's not on bipolar, on introversion, extroversion, and other things. Greatest athletes, greatest rock and roll musicians, all kinds of research discussed elsewhere. Consistent, clear, the theoretical framework is beautiful. That's what this is all about. So sometimes when we're talking to the cynics of astrology, and they'll say, oh, well, your control group, your hypothesis test did not have enough people. Well, true. It didn't do true. It's not a game of us saying, oh, we've got the proof of astrology. No, this is a game called evidence-based practice of building a solid theoretical framework, of building an accumulation of data, assessing what it's telling us, and it's telling us it's more likely that astrology produces measurable effects than not. That's shocking. That's shocking. If that's true, that changes everything in academia. That changes psychology, medicine. Whoa, a whole new set of variables that it looks likely that they actually exist? We don't know for sure. This is worth pouring a lot of time and energy and resources into finding out, which we've done. We've created Cosmobiology Institute, so we're on our way to doing this. So a technical note, excuse me, for anybody interested in getting into all the details, these are the means for each of the accuracy ratings and the number of people who have those accuracy ratings, 69 total. I've got a typo here. 69. This shouldn't say AA accuracy only. Oops, sorry. It should say all data. Sorry, right up here. It should say all data, C or better, B or better, A, and AA only. So a little typo there. Wasn't thinking. Anyway, these are the means that I gave on the previous slide, and these are the means for each control group, and this is the mean of those control group means, and so the final value. Just in case you're wondering, and if you replicate the study, you can get the data, replicate, except for the 8 charts from Giselle that are confidentiality. So we can't share that. But the rest, I've shown you the names, and it can be replicated. Hopefully we'll be collecting more data and doing new tests anyway. Some final notes. We created the AstroSignature, again, as you know, by comparing the scores of 912 people with bipolar disorder with a shuffled control group. I want to underscore the point that a shuffled control group is very conservative. It's more similar to the actual people with bipolar than any group of people. You could select 912 people who are, doctors, lawyers, students. The distribution of those charts throughout the year, throughout the day, the places they're born, is going to be different. That's going to create different probabilities of planetary configurations. the shuffled control group is so similar to the actual people with bipolar disorder that if you find a difference, you probably really found it. It's a very extremely conservative control group. And the test I did happened to be a two-tailed test, just to let you know. And we reached 5 sigma, 5 standard deviations difference. It's huge. And I showed you the formula. It's fairly elegant, not perfect. And we use the same weights and same orbs for everything. So I'm just summarizing some key points. And I want to summarize this point again. There is a balance of having an elegant AstroSignature, an AstroSignature that's consistent with theory, supported by previous research, and a very low p-value. If you only have variables in your AstroSignature that you understand the theory for, that are supported by previous research, it's going to be hard to discover anything new. There are things we don't have a theory for that we didn't know, so you want to be a little flexible, but you don't want to be so flexible that you just completely what we call overfitting. And so we made some compromises, you always have to, from what we thought would show promise. And as I mentioned before, we can create alternative models from that data and see how they work. Okay, that's it. We're ready for part 7. And I'm going to show you some really cool things in the next sections, how we confirm the model using forecasting. So in those 4 stages of research, there are some additional things we did to validate that I didn't talk about yet. And I want to show you the confirmation by forecasting because it's so totally cool. So I'm going to show you that in part 7 and a few other things. Okay, thank you very much for listening, my friends. God bless. Namaste.